nicely into the next the next theme. Scalability. So yeah, as you mentioned, Hydra is one of the avenues, and to look at scalability on Cardano or Ouroboros on the eUTXO model. Maybe before we dive into that, some definitions again. So, Cardano uses the eUTXO model.
Yep.
Bitcoin uses the UTxO model.
In fact, yeah.
Before we go any further from what Ethereum is, how do we differentiate, or well, maybe we should start with UTxO versus Ethereum. So that's Orderbook model. And how would you define both?
So the Ethereum model is basically your bank account model.
Yeah.
Right. So you go to a bank or you go to Ethereum blockchain and you open an account.
Yeah.
That account has a balance, and then you can transfer from that account to other accounts, or you can receive funds from another account. And then in Ethereum, smart contracts introduced into the picture by saying there are two types of accounts, what they call external accounts. That's an account for a human, or at least one controlled by a public key, and usually it's used by a human. And then there are script accounts. And the script account doesn't have a public key signature which authorizes payment from this account, but it has a piece of code, the smart contract, which can be sent messages, it can receive messages, and it processes these messages. And as part of processing these messages, the computer code which is executed processing these messages, this is what we regard as Ethereum smart contracts, and they can transfer funds, do other things.
Right.
So that's the account model. Now the UTxO stands for unspent transaction output. Model is based on the idea that we have got, and maybe I can use a picture here. We have transactions, and transactions, they have multiple inputs and outputs. And so an input is funds which are being paid into a transaction, and outputs, that's funds being paid out of a transaction. So when I create a new transaction, I consume, let's say, two outputs from there are other transactions here, right? I consume outputs from previous transactions. Then I've got my new transaction, and that new transaction can produce one or many outputs, right? So this one creates 4 new. It eats, destroys 2 old outputs from other transactions, and produces 4 new outputs.
And what you don't mean by output or input is that, or no, you're just talking about outputs here. So let's say these 2 outputs is not 2 Cardanos, right? Those are not 2 Cardano coins, but these are just 2 outputs from a former transaction.
Exactly.
Yeah.
And
so it could
each
be any amount.
Transaction can have an arbitrary amount of ADA.
Yeah, exactly.
And in the basic UTxO model, which is what Bitcoin uses, would be Bitcoins, then this is the only thing that can be in an output, which is then consumed by an input. So if you like, if we have another transaction which then consumes this input, so it's every output becomes then an input for a follow-up transaction, right? Yeah. So that's how inputs and outputs relate to each other.
Yeah.
And the unspent outputs, that's the one dangling here. They haven't been consumed by another transaction.
Yeah.
Right. So this is what UTxO stands for.
Right.
And instead of having a notion of account in the UTxO model, we only have a notion of unspent outputs. That's the stuff I can still spend. And transactions, which are only one thing. They consume outputs by inputting them.
Yeah.
and produce new ones.
Yeah. Okay.
So that's the
Fundamental
structural
difference.
difference between these two models.
Yeah. Okay. And so, yeah, Cardano uses the extended UTxO. So that additional step from the UTxO model to the extended UTxO model, saying very simply, is the ability to add smart contracts, right, to the Cardano or the Ouroboros protocol.
To the ledger rules, yeah.
To the ledger rules, yeah.
So this is basically what I mentioned in the beginning, that together with Phil Wadler, I was building Plutus team and so on. This was really one of the core questions for us in the beginning. Cardano already had settled on the UTxO model. Why? Well, the UTxO model has several advantages. One of being security. I mean, this is of course an unfair comparison, but if you compare security incidents with Ethereum, Bitcoin, then you know where you should store your money, right? So the idea here to use the representation with the better security track record. Let's put it like that. Right?
Okay. Yeah.
And but one reason why Ethereum switched to the account model is because they felt it makes it very clear how to integrate smart contracts. Because, as I said, you have these two sorts of accounts, and you just have accounts which are governed by a contract, and that's the way to integrate contracts. So it makes it easy. Now, Bitcoin actually already always had scripts, but what we call Bitcoin script is a very limited programming language. It can't do much. And where do we need this? And this is where it comes in basically in the connection between the inputs and the outputs. There are two ways of permissioning, of determining whether somebody is allowed to spend an output. That's a very important question because remember, these outputs, they carry money.
Yeah.
So can I spend it?
Yeah.
Is equivalent to can I get this money? So you really want to be sure that's going right. So one way this can be determined is by using signature of using public-private key pair from within your wallet. So that's what Bitcoin usually does. This is what Cardano did before we had, well, Cardano is still doing it, of course, but which was the only way to spend money before we had smart contracts.
Yeah.
But the second approach is, instead of using a public key to make this decision of spendability, we use a computer program. And now the question for us was, well, when we have this account model, these computer programs, these smart contracts, they really have a view of a lot of information, right? And they can themselves use other code in other smart contracts of other accounts. But in Bitcoin script, the original Bitcoin script, all the Bitcoin script could look at is the output it is spending, so the value basically, and then some little piece of data which is part of the input. It is what we call a redeemer, which is just some data which is being used as part of the process of convincing the script this can be spent.
Okay.
So this is very little information.
Yeah.
You can do a few simple cryptographic protocols with that, which we know from Bitcoin, like hash locks, time locks, simple decision procedures, but nothing complicated. So our question, scientific question in the beginning was, how can we generalize this structure of the UTxO model to give computational capability which is comparable to what we've got on Ethereum? Or
better.
Comparable as in with computation power, there's a limit. That limit was set by people like Alan Turing and Church, as like having the full capability of what a computer can do in the first place.
Right.
So once you reach that, that's it.
Okay.
Yeah. So that was the question. How can we do that?
Right. The choice then largely for the UTxO model was its security, right? That was a large part of the consideration.
Mm-hmm.
And now moving to scalability. So, there's certain advantages that the Orderbook model has, but also for the UTxO model, it has it's definitely the security aspect. How does the scaling of that model work? So also between Bitcoin and eUTxO, when you talk about scaling, what are some key differences to keep in mind? So for example, I take it with eUTxO, there's a lot more heavy type of processing, right? That's being requested of the blockchain network. So just quickly looking at the differences in scaling between how UTxO would try to solve it versus how Orderbook model would try to solve it. What can you say about that?
So maybe I should begin in how we extended the Bitcoin model. Basically, we gave those scripts which decide whether a connection is allowed, whether you're allowed to spend those outputs, get those money. We extended it with two things. First of all, originally in Bitcoin, only money, Bitcoins, in our case ADA, were flowing across these input-output arcs. But we added data. So we said, okay, we can have value, monetary value, flowing across this network of transactions, and we can have data flowing across this network of transactions.
And by data, you mean?
Arbitrary information. It can be, this is determined by the smart contract. It can be the state of your contract.
Okay.
In a crowdfunder, how many people have already paid in? That kind of information.
Right. Okay.
And the second thing is that this script, which is being run here to allow or disallow this connection, gets the entire, this is what we call the spending transaction, the transaction which eats up the output and gets the money. The spending transaction, the script in the extended UTxO model can see the entire spending transaction, including maybe there is there's another input here, which is actually getting its input from a completely different transaction, right? So that script can also see this input, and it can see all the outputs, because we have outputs here as well, right? So it can see all that information, and that gives it a lot more context. It knows where all this value and data is going, and there's data flowing across the network in the first place. These are the two fundamental additions of the extended UTxO model. What's also important is what we didn't change. The structure of this network, in computer science we call it a graph, of this graph of transactions did not change. And so all these properties of this graph, of this network of transactions, which Bitcoin had and which are very valuable and which are allows us to reason about these transactions in a mathematical way. All these properties, these mathematical properties of this network of transactions are fully preserved. So this was one of the core ideas here, because if you go to the account model like Ethereum, you destroy a lot of information.
Why?
Because accounts, there's one list of accounts and it's global. You never know which account is interacting with what other account.
Right.
But with these transactions here, we can look at the connections and we know which transaction is connected with which other transaction.
Right.
And we know only those which are connected can influence each other. Okay. So if you want to write up in mathematical terms What happens? How does the value, the data, the information flow here? This maybe not super simple, but it's relatively straightforward given introductory computer science knowledge to reason about the data flow here.
Okay.
Reasoning about the data flow in the account model is basically impossible. There are ways you can approximate it, but it will always be an approximation, can never be perfect. And that means a lot of analysis, a lot of reasoning about what happens in the account model is much, much harder or even impossible compared to the UTxO model. So we come back to this. We need to have mathematics at our disposal to reason about our systems. Otherwise, we don't know whether they're secure.
Right. And I mean, this sounds like there is this data richness on the eUTxO, UTxO model that the account-based model then perhaps doesn't have. Does that mean that there's also, the flip side of the coin, it's a lot heavier, so there's a lot more data being created?
The account model also can store data. I didn't mention it, but in the account model, when you have a script account, you have whatever ether you've got in the account, but then there's also kind of like a memory component of the contract where the contract can store arbitrary data in the account. So in that sense, this is similar. But what's different, and coming to what you were asking about with respect to scalability, actually we've got a big advantage here with the UTxO model because the interaction is clear, so we can cut out sub-networks or sub-graphs, right?
Okay.
And it is always clear how to organize computation in such a subgraph. But if you have a list of accounts, you never know which account is interacting with what other account. So if you want to do anything, what's called sharding, or want to do off-chain computation, like in a layer 2 protocol, like in Hydra, then determining which subset of the accounts, what subset of the data, the information, the value do you take into an off-chain computation is a lot harder to do in something like an account-based model. Whereas in this network of transactions, we can always collapse such a sub-network, we call it subgraph. You can always take out a subgraph and have this as a sort of super node, a super transaction with all the inputs to that subgraph and all the outputs to that subgraph. And this is the idea behind Hydra. In Hydra, you take of all the available unspent outputs, you take a subset, a bunch of those, and you take them out into this off-chain protocol, do computation on them really fast, really cheap, and then you put them back onto the main chain with cryptographic proof that you did the right things off-chain.
So just before we get into that, just so to make sure that I understand it also a little bit, is you have this, the richness, right, by which you can assess where the information flows, how they came from the one unspent transaction to the next, how the state changes occurred during that whole process.
Exactly.
This type of information, the richness that the UTxO model has, is the same strength by which you can build scalability methods that you could not build on a Orderbook model, like Ethereum
account model.
Model.
At least not in this way. I mean, when you have something like the account model, then you always need some sort of analysis. Which smart contract of one account is calling all the other accounts. Now you can look at the code, but that only gives you an idea of which could be called in the worst case, because you never know. The next call to a smart contract may do something different. You don't know which code will be executed and which calls to other smart contracts will happen in the future. But with a set of UTxOs, you know this is the set of UTxOs which you can take, which themselves is a UTxO set, and you do computation on. And they are basically, it's more local. It's more compositional. So it's easier to cut up into subparts, which are then looked at individually.
Right, Hydra.
Yeah, exactly.
So with Hydra, this is your your baby, right?
Well, it's our baby,
Oh,
the
yeah.
Hydra team, but I was involved in it.
Yeah, of course.
I certainly don't want to claim
but
all the credit here.
yeah, no, of course, and all those names are also on the papers, right?
Sure.
So yeah, scaling then for Cardano. So as you say, like bundling together, this is how Hydra would work. So yeah, so maybe I interrupted you before on just trying to clarify, this data richness. Can you explain Hydra in short?
So Hydra. So one common misconception with Hydra, and maybe this is on the basis of our imperfect communication. There's not one Hydra or one Hydra protocol, but Hydra is a family of protocols. Why? Because there are different scenarios which require different protocols. And this is easily explained. Imagine there are, for example, stake pool operators which need to exchange information or value between each other. They are always online. They have to be always online because maybe they have to produce a block in a minute.
Yeah.
They have a relatively rich, let's say, computing environment of a certain storage and processing capability because they need to be able to process the chain. They need to follow the chain all the time. And when they're being selected to produce a block, be ready to deliver this block to the network, right?
Yeah.
So this always online, having the capability to run a full node property is something SPOs have. And if you want a protocol where SPOs can do computation among each other quickly and fast, then you can use those properties. But if we look at end users with maybe even a light wallet on a mobile phone, it's a totally different story. The mobile phone, first of all, you can't run a full node on it. Secondly, it's not always online, maybe runs out of battery in 5 minutes and it takes 3 hours until I get to charge it, right? So maybe it's not online for a while. And with cryptographic protocols, which are outside of the blockchain, so what we call layer 2 protocols, whether the participants are always online and whether they can run a full node makes a big difference. So we can't have one Hydra scaling protocol which works for everybody because the different participants in Cardano have different properties with respect to their online-offline status and with respect to whether they can run a full node or not.
Okay.
And so, for example, the first protocol which we've published in the Hydra family is the Hydra head protocol. The Hydra head protocol is designed for SPO type of entities. It assumes that the participants in a Hydra head, that they're always online and they quickly react to messages between each other. And so that's fine for that type of participants. But now if you want to add some random person on the mobile phone, that's not going to work anymore because the others will have to wait for that person to maybe be online tomorrow until they can do the next step in the protocol. And so you need a totally different protocol where somebody can be away for a long time, maybe a week or maybe longer, and still the security properties of the protocol are such that the stronger parties in the which are together with them in a contract, say, can't cheat them.
Right.
This is the difficulty. Even the computationally and online stronger party shouldn't be in a position to cheat on the little guy.
Yeah.
And that's difficult computationally cryptographically. And that's why we need different protocols.
Right. Okay, so you're saying you need different Hydra heads?
Different Hydra protocols. So head is one protocol.
Yeah.
That's for the symmetric, lots of SPO type of entities protocol.
And you need different Hydra protocols to ensure that there's no one Hydra protocol that behaves in a manner that the network doesn't really want, right?
Yeah, and of course it would be great if there was a protocol to rule them all, right? That'd be great. But looking at, we are not the only people who do research into layer 2 protocols. In fact, it's a very rich research area, and there's a lot of existing work as well. But one protocol which does everything, like strong entities and weak entities, but at the same time fast and instant confirmation, everything together doesn't seem to be possible. I give you an example of a different protocol, the Bitcoin Lightning protocol, which is a pure payment protocol. It's different. First of all, it's a point-to-point, so it's only two parties. And it's not necessarily between two parties very fast, because individual endpoints can go offline for a week or so. And in that time, they don't have to worry about being cheated, because the other person can't do anything very quickly without them. And then Lightning gets its capabilities through having many of these channels organized in a network. So that's a different setup, but where you can tolerate that some people are offline days at a time.
Yeah.
Right? So you see that depending on what type of participant you're dealing with, you need different type of protocols. And nobody has found the rules them all protocol, which is still fast and still instant settlement and still cheap. So we have to do with having different protocols for different situations. It's like, well, sometimes you need a small fast car and sometimes you need a truck. And there's no way to have both at once, right?
And if we do find a way to get all of them together in one single protocol, then stay tuned to AmsterdamNode, because we'll tell you.
The one protocol.
The one protocol. Okay. And touching back also on what we were talking before, right, about the scientific approach and now the scalability challenges that Cardano sees. How and you've seen this from start to finish, right? You've been there at the beginning, very much at the development of Cardano and the protocol of Ouroboros, and those papers that were written at that point in time versus where we are now, how the network's being used, what the behavioral state is of the network and the individual actors inside of it, the behavioral economics part of it, right? If you look at where the research pointed as a future state or what it wanted to develop versus what we see today, how do you relativate those two? Like, what do you see that those papers got right, let's say, versus these are the ways that there was something unexpected happened, right? That we need to account for, that we need to re-research, or is there something you can say on that regard?
Yes, of course. Always with a research paper, you've got a particular problem you try to solve, and what we call applied research, and a lot of research we are doing would fall into this category of applied research. You've got already an application in mind. Sometimes you do foundational research, then it's just trying to figure it out. It's just about making humanity smarter. But applied research has a kind of like, we probably want to use this for this and that. And this can go wrong, or it doesn't go wrong, but it can be not fully satisfactory in two ways. Sometimes the problem is just harder than you thought, and it just takes longer. an example out of Cardano is we thought we would have sidechains earlier. But sidechains turned out to be harder. I mean, to a certain degree, actually not so much the basic cryptographic protocol, but yeah, there are things around it. So just to give you an example of difficulties, I mean, it's one thing to have a protocol for a sidechain, proof of stake sidechain, right? Which once it's operating, everything is running fine. But there's a additional question which may not be answered by the protocol itself, and that's how do you start a sidechain with proof of stake? Proof of stake has a bootstrapping problem, generally. Namely, when you produce the first blocks,
what you said,
either nobody or one entity has all the stake. So, or you have initial, whatever is in the Genesis block, a few people, like the stake distribution in the beginning is anything but broad and decentralized, right? You kind of start with a centralized system. So in Cardano itself, we've solved this by starting in this federated mode and then slowly decentralized. Remember with Shelley how the decentralization went further and further until we were 100% decentralized, right? But it's an incremental process. So bootstrapping a proof of stake chain is difficult, and bootstrapping proof of stake sidechain has the same fundamental problem.
Okay.
And then the question is, how do you do that? And yeah, I mean, these days there are possibilities, like if you attach it to if it's a side chain, maybe you can use the stake of the main chain to secure the side chain. It's one way, but it also has potential pitfalls because maybe over time the stake distribution in the side chain is quite different in other tokens, and then what does it say about the security of the sidechain with respect to the main chain's different stake distribution? So there are questions like that which are not directly about how does this protocol work, but they are more like in how do you set up the whole system.
Right.
And often you do a piece of research, you have a protocol, but it's these environmental factors which make it more difficult to actually use that protocol in practice than what you thought. And that's a typical way in which things can be hard. But the other thing is, maybe you develop a protocol. For example, in the Hydra suite, we have a second protocol. It's called T2P2. And
I like the name.
And it's a pure payment protocol. So it's like Bitcoin Lightning, but it's not a network of channels, but it's one server which can handle lots of clients which want to pay each other. And it uses state machines and hierarchical states. It uses a lot of cool tech, right? But it has, on one hand, once you do some payment thing like that, and in our case, we have a very strong property. Clients can be offline however long they want, and they still can't lose money.
Right.
But then you pay a price. So on one hand, you have to have deposits like Lightning. If you create a Lightning channel, you have to put some Bitcoins into it, and that's the amount of money you can let flow over this channel. And the other thing is, it's cool, the protocol, but it's also quite complicated. And what that means is we have a Hydra engineering team as well as a Hydra research team. When the Hydra engineering team looked at it, they were going like, oh, who's going to implement all this, right? So you've got a protocol, you've got to prove that it's secure. What does it mean it's secure? Do you have certain security properties, and you've proven these properties in a particular adversarial environment? And but then somebody has to implement all this, all right? And sometimes this is just a lot of work. Takes a while. So these are kind of the two ways in which you do the research, but then it may require further work or take a while until you get to a product because it's hard to implement or because of these environmental factors.
Okay. And what, I mean, of course, everybody will ask or be in their mind, okay, so scaling, it's coming. How, when, what, is there anything you can say about that? About when will people that are using these different DEXs, right, with their different various wallets that everybody has installed, but they all come into the same problems, but even those who run a full node see those problems as well, where there's like basically this growing waiting list going on for your transaction to be executed. When will people see a noticeable change, right? So like, how is these new developments going to influence?
So this is really continuous process. So we have, on one hand, we've been very defensive in the release of Cardano with protocol parameters because it's kind of security first. The ground rule is it must be secure. Yeah. And once it's secure, we can make it faster, but we can't go the other way around, right? Yeah. Once we break security, we're done. That must not happen.
Yeah.
So with the security properties of Ouroboros are based on certain speed of propagating blocks through the network, and so they're based on timing properties. And so with the size of blocks, with the amount of script execution inside of transactions, we were conservative and using values where we thought this is definitely going to be within the bounds of what's secure. But because we were conservative, actually, there's a lot of leeway at the moment between for example, block propagation time and how long it could take and still be secure. So, and we've already seen that in that the block size has been increased to 80 kilobytes. The parameters for memory for Bluetooth scripts has been increased. So some of these parameters have already been increased, and this is going to continue throughout this year, that we will relax parameters, chain parameters, to slowly fill up to the point of where we are still secure, but we are using all the headroom we've got for block propagation generally.
So from just a conceptual point of view, how I see that then is that as long as there's enough pressure in the valve of block propagation, right? Then you can start, let's say, opening the valve more, right? So that the pressure is important. It's important for there to be a high density or whatever the word is.
It's more the speed in which blocks propagate through the network. The problem is when a block gets bigger, then just transmitting it over the internet takes longer, and checking the block validity. You have to see in the Cardano network, when a block goes from node to node to node, every node has to validate it. No node may take a block and say, the other guy said it's okay, let's just pass it on, because the other guy may be the adversary, right? Trust nobody, basically. So this time to validate a block and to just do the network communication is basically limiting how fast we can get a block from Amsterdam to Sydney, right? And that has to happen within a certain time period. And as long as the blocks propagate through the planet in sufficiently quickly, we can make them bigger, which means the network transfer will be taking longer, and means because it's bigger, it has more transactions. So checking that the block is valid also takes longer for every node in every hop. So it's really a matter of how fast to get blocks from the block producer to all the other SPOs. That's really the limiting factor here. So that's one thing where we are steadily kind of allowing more transactions and more expensive transactions up to the point where it's still secure, but we use everything we've got out of how fast the internet is and how fast hardware. I mean, these are the two things we have to work with, right?
Yeah.
But the other thing is a blockchain is a huge planet-wide distributed network, right? Distributed systems are hard. It's very easy to write code for distributed system which doesn't work in certain situations. And again, for blockchain, it must not go wrong, right? So again, we have to be start on the safe side and then get more ambitious.
Yeah.
And one way to make a distributed system more obviously correct is by doing things one after the other. So instead of lots of different parties doing things at the same time, we let one person do something, another person, and this is how blocks are produced, right? You know, there are lots of SPOs and they get assigned one after the other. You produce a block in this slot, you produce a block in this slot, you produce a block in this slot, right? They do round robin, create those blocks.
Yeah.
But if they all could create blocks at the same time, we could create a lot more blocks, right? So, but if we all do it at the same time, it's a lot harder to make sure it's correct. So what we are doing, this purely sequential process, we're slowly making more concurrent, more parallel, more doing things at the same time. And one of the things which has been talked about is pipelining. Pipelining means we don't check a block is correct and then pass it on, but we check that the block header, which is only part of the information, is correct. Then we pass it already on while we check that the block is correct. So some things which used to be one after the other, we start to do at the same time. And that means we can, again, propagate blocks more quickly from Amsterdam to the rest of the planet, which means we can stick more stuff into a block and we can allow more script computation to happen.
Okay.
So by doing these things on multiple fronts continuously, we can, over the course of this year, increase the throughput of Cardano mainnet. This is no Hydra, nothing. It's just mainnet, quite dramatically. And this is the first thing to do.
Okay.
I mean,
and what is dramatically? What does that mean for, let's say, the people on what is it? Let's say Sunday Swap. I think was one.
DEX. Yeah.
DEX, right?
Yeah. The first DEX.
The first. Well, isn't the first one? Was it Muesli Swap?
Maybe Sunday had the first beta. Okay, I don't want to.
Okay, yeah. Don't rock the boat. But,
let's look it up on the internet.
But yeah, so for people using Sunday Swap, let's say, they are standing in line, right, for their AmsterdamNode token. And how that will be significantly changed with these parameters that are...
Yeah, it's going to be several times faster. Now, how much faster is something people argue about. There are optimistic scenarios and there are less optimistic scenarios, which depend on, I mean, these things do depend on network traffic speeds. And we've done a lot of simulations, like renting AWS instances across the planet and running experiments and so on.
Okay.
But I mean, this gives you some experimental data,
right.
But at the end of the day, once the system is complete and is deployed, we have to measure what's happening and then we have to see. So we have estimates and we have what we think are, this is minimum what is going to get us. And then we have optimistic scenarios, which are much better. And there's recently been a blog post. So the last one was by Matthias Fritzi, who's one of my researcher colleagues.
Okay.
Also one of the Hydra people.
All right. Nice.
And you can find it on the IOG blog. So iog.io. Go to the blog and look for blog post, I think was this month or last month by Matthias Fritzi, and it has a table with various scenarios. Also depends on what kind of transactions have you got. Is it transactions with a lot of scripts, transactions which are small, transactions which are big. So that
this is it, no? Okay, so here Matthias Fritzi, and here this is...
He's explaining it, and at the end is a table with various scenarios, and this is still the more pessimistic one. So
this is what you mean?
Yeah. So browse the first row.
Yeah.
Browse is the current implementation.
Yeah.
Browse max is where I said we have the same protocol, but we use all the headroom we've got.
Okay.
So without changing the implementation of the node, but changing protocol parameters, this is what we think we can get. This is browse max.
So this is...
And this is the various columns are for transactions of different size. So there's always this kilobyte, that's the size of the transaction. And then a time, this is how long it takes to execute, how much script execution time is in there. So the first column is basically a simple payment.
Yeah.
And the rightmost column, that's your Sunday swap transaction, where there's a lot of stuff going on. And
okay,
then
but that doesn't increase in speed then.
Yeah, so for browse, if the script execution time dominates, it does make a big difference. But if you go one to the left, you see a bigger transaction.
Yeah.
It already makes a huge difference, right?
And what does that mean in practical difference? You know, a big transaction?
It's not a 2 kilobytes transaction. Has more inputs and outputs, longer thing.
Right, but it's
but
not
the
a smart...
milliseconds is how long the scripts for all the inputs of the transaction taken together, how long they run.
Okay.
So whether they run half a millisecond, 2 milliseconds, or 32 milliseconds, which is the max more or less at the moment. And
but is this then that people for waiting on their Sunday swap transaction during Frauos max will still be waiting for their Sunday swap transaction?
Well, the thing is, not all transactions which go into blockchain are Sunday swap transactions. Right? The Sunday swap transaction is one among many.
Yeah.
If you accelerate everything, but a scenario where you had only Sunday swap transactions. So if you had only nothing else but Sunday swap on Cardano, Cardano Sunday swap, then with browse max, you wouldn't see a difference.
Right. Okay.
But given that there's lots of other things in there, it still makes a big difference.
Yeah. Okay.
And then if you go to the next one, pipelining is what I said, where you overlap validation of a block with transmitting it. There you see improvements through everything across the whole board. And then AV, this is yet an further parallelization of block validation and propagation. Then you get even higher increase of throughput.
Okay.
But the important thing is we are talking about here really, this is factors. It's not 20% more. It's 4 times as many, right? So we are really talking about factors of increased throughput. And this is all without layer 2 of, this is really just main chain throughput, right? Base throughput. And at the same time, we are still working at Hydra and everything. This is not to substitute it. It's just to say that even on the main chain base protocol, there's a lot that's going to happen there.
Yeah.
Even without looking at all at Hydra or other technologies.
Okay.
Right.
Okay.